Okay, cool. Yeah, so generative models are kind of how do I say this? A nuclear weapon, but with the positivities of nuclear energy. And it's important if we're going to start making nuclear weapons that we also make sure we don't blow each other up. Not to be that doom and gloom about it. It's just at the beginning stages of everything. But yeah, those are generative models, and GANs is one specific generative model. So for example, the DALL-E E2, that uses diffusion models, which is a very specific type of generative model. And then, as I said, the transformers and a whole bunch of other stuff like VAEs, et cetera, et cetera. The reason I'm so focused on GANs is because they do provide a lot of benefits that my PhD is trying to persuade, and I'll get to that in a second. So GANs were introduced in 2014. They were kind of one of the first big tech hypes of AI. It was introduced by Ian Goodfellow, who moved to Apple, generally to improve image quality. So they actually have GAN chips, or chips specifically designated for GANs, to improve the image quality that comes into your camera, which means you don't need a very high-end camera for a high-end image. But then Ian Goodfellow left there because of return to office policies or something stupid. But that original GAN paper has over 50,000 citations, which doesn't even comprehend yet, because if you just do a GAN search on Google Scholar, not even Google Scholar, you get 112, 115,000 results, right? So these are these things. The same thing happened with transformers. You get this one little revolution that just pumps every single researcher into that direction. And GANs is one of them. There's a whole lot of applications. There's a whole lot of variations, reviews, etc., etc. But they are still kind of people tend to not want to touch them because they are quite difficult to do anything new with. So, for example, the transformer, as Ron was speaking, is very specific, and you can try and alter the architecture and get something new out of it, or you can try and change the tokens and get something different out of it. You can put the images into tokens. For GANs, it's like plug and play. This one worked. Oh shit, that one worked. No one really knows why, and everyone's trying to figure out why. But eventually they will get there, in my opinion. So the problems are the stable training. There isn't a guaranteed convergence, and my PhD is about improving the cost and practicality for applications specific to GANs. So I don't actually look at generative modeling. I look at the other side, but we'll get there as well. Cool, so just an agenda for this tutorial. Introduction to what generative modeling is at a foundational level, the what, the why, and how. A very layman's explanation of how GANs work and how they train. And then we can go into the coding of it and have a conversation at the end. And the coding as well, I'm just going to give very vanilla coding for it. You can find the code on TensorFlow. It's one of their tutorials as well. But it's important to so generally when you use like model.compile or model.fit for TensorFlow kind of applications, you can't do that for GANs. You have to go a little bit deeper into it. And I've been doing that since 2017, which means I was even deeper than that, but they've made it a lot easier. And so you can go home and very easily code your own little baby GAN. Cool, so generative modeling by its foundation. So you have your training data. It's unsupervised training data that you don't need labels with this stuff, but if you have labels, they can actually improve the modeling. And the job of just given a neural network is if you have input noise, so you have a random normal distribution, you can choose what the vector length is, and it's just noise that goes into the network. Then you have the black box of mathematical transformations, and then the output of that neural network should be the same as the training data. So in essence, you have a generative model that needs to match the probability distribution of the training data. And why I say match the probability distribution is because there's also a specific criteria for generative models, in that no image can be a direct copy paste of the original training data, because then what's the point? So these models need to go very deep into what they call the lower dimensional manifolds of the training data and really learn the nitty-gritty stuff of the data so that it can generate something that is photorealistic, that humans can't tell apart from the real training data, that another model can't tell apart from the real training data, and then you've got your convergence. And yeah, by the way, everyone, you can stop me and ask questions throughout. It really doesn't matter, but we also have time at the end. So for some of the applications for generative modeling specifically, so as I said beforehand, you can improve the image quality. So instead of putting noise into your generative model and then expecting a random image at the end, you can put a low image quality into your neural network and then expect a high image quality at the end. Which means that most of our photos that are on our phone don't come directly from the camera technology because how much AI there are putting on our phones. So that image is being upgraded by a generative model. Whether it's GANs or not particularly the point, but that's one of them. And then beyond that, so it's smartphone cameras. You can do the same thing for satellite images, which is a very important or very difficult task because to get a camera into space that can take high quality images at very low resolutions, say like 1 meter by 1 meter square, very, very difficult. So if you have a generative model that ups that quality, you get something out of that. Same thing for medical images. Think of a brain scan. What happens if you don't have the highest end brain scanner? Use a generative model to improve it. There's a couple of nuances when it comes to that because you're technically using a statistical model to improve, say, a brain scan, but then it could also like make something wrong and say there's cancer where there isn't cancer. So there are some nitty-gritties to that, but that's the improving of image quality. Then you can also increase your data set size. So everyone knows for neural network training, you need a lot of data. If you don't have that data, use a generative model on your little bits of data and then increase your training data set size before you train your classifier or whatever you are trying to train. Especially with imbalanced data sets, that helps a lot as well. So there's something called a conditional GAN, where you tell it, okay, so for example, for the MNIST images, a conditional GAN says, give me the class of that image as well. So then you're going into a supervised problem, not an unsupervised problem. Now, if I give the class to the generative model, then later on, so you give the class and random noise. So you say, please generate a image that is specific to that category. Information as well. And then that helps with the imbalanced data sets. Make me more samples for the specific category because I just don't have enough of them. And then what I'm looking at is the improving of the artificial learning capabilities. Label data, because finding label data is actually the biggest hindrance for neural networks in practice. And then because you're doing semi-supervised learning, you get more precise lower dimensional manifolds. And then what I'm looking at is less overfitting and doing a bunch of other stuff. So that's the why. More specific applications, as the video mentioned, the artistic endeavors. There's an art museum that opened up in, I don't know, San Francisco, New York, California, I don't know. That was completely AI generated images, an entire art museum. There's the DALL-E 2, which is you type in a text and it gives you an image of what you typed. A unicorn with a girl sitting on it under a rainbow. Boom, gives you that image, right? And it's photorealistic because that thing trained off, I think, the entire Google image database or something, or not the entire, but like a lot of images. Then there's the super resolution thing I was speaking about, so low resolution to high resolution. Then there's the other side to the stuff, which is the fake videos, the deep fakes, the social media. So there was a conversation happening, what was it, 5 years ago, which was the hype of AI conversation, at least if you were part of it. What is real, what is fake? I don't know if, hopefully most people in this room can to tell a fake article from a real article online nowadays, just because you're looking at the right sources. But you can use a transformer just to write a completely fake article and see how many likes you get. And there's a couple of regulations and stuff that's gone into social media that can like stop this, but it's still there. I can still write an entire book and become famous because I trained a transformer, right? And that's problematic, at least in my case, in my opinion. And the deep fakes, so there is already a deep is our next weapon, if you want to call it that. Then there's the side that I wanted to speak about philosophers too, which is actually quite interesting. So when it comes to fake videos, if you think about it, if you stop people from doing this. If you give me every single TikTok video in the world, then I can just generate fake TikToks, which means that every single time you scroll on TikTok, you actually don't know if that's a real video or not. Considering how far China is in AI, I might actually say most of those videos are fake. And that's something that like boggles your mind, because you're thinking there's someone out there taking a video of themselves, but it legitimately could be fake. And now take that conversation a little bit further to philosophy. Is what happens if we have smart glasses on? What happens when you have eye contact lenses in? We are literally able to create simulation theory and make it practice. Simulation theory is the matrix. Are we destined all to sit in our rooms with eye contact lenses on and pretending that we're in somewhere where we are not? I'm biting my ass off to make sure that doesn't happen. But not everyone's listening, so politics is next. But yeah, so we literally have the tech and the foundation to create the matrix. And that's something that we have to take quite seriously, because the matrix is, by essence, the loss of you, the taking over by robots. And everyone in the machine learning community does tend to say, that's fine, the metaverse is dope. I'm not a fan. And go look at the mountains and the stars, please. It's very semi-supervised learning stuff. Cool, so here are just some examples. Ancient Chinese paintings, completely recreated by a GAN. Can't tell it apart at all, and wins prizes by people for the artistic community. Not that we're in that community, but that is problematic, because if tech people start taking over art, it's just two worlds that are not supposed to be bridging. Super resolution, so here's a couple of examples. You've got your original image in the beginning, and then your output is just a higher def image. So generally what it does is it looks at pixel-wise kind of stuff, and it just tries to, like, looks at patches and everything like that, and tries to just up the def of that image. And as I said beforehand, the kind of applications for it with satellite images. So there's actually I'm looking into this specifically for classification of these things. But if they're low def, you can't really classify anything. So the idea of making them high def fits in there. But then, for example, if you look at that middle image, if you can detect pests on those farms before they spread, specifically because satellite images at a pixel level is a 1 meter, generally 1 meter by 1 meter square radius. It doesn't have to be satellites, can be drones as well. You can detect that pest and go kill that pest before it spreads and kills everything else. And then there's also military connotations to that. Everyone's using military satellites to spy on each other, and then they're going to start using GANs. And then the other part that I'm looking at as well is detecting cancer on brain cells or brain image. I'm not too much a fan, as I said, of using higher definition for this kind of stuff, because you're supposed to get very intricate with where the cell is and where the cancer cell is. But when we get to the classification parts, very interesting, because if I can pick up exactly which pixel, which could be a nanometer by nanometer, which pixel has a cancer cell, and I should be able to blast a laser or at it and just kill the cancer, right? So we're getting to a point where we've got this very dangerous tech, this nuclear weapon that has a lot of positive connotations, like a lot. These are just two that I'm looking at, but the further you go into it, the further you go into medicine, the further you go into any applications when it comes to classification in general, there's a lot of positive things that we can do. And considering that COVID made the amount of doctors apply to go study less, we're going to end up in a healthcare sector issue as well. So we might have to use these things. Cool. Those are the applications that I wanted to mention. The idea that the world's going to end and the idea that the world's going to be saved, both clashing each other. That's kind of my vibe. People call me a doomsday prophet, but at the same time, you need people to kind of climate change people are also doomsday prophets. Okay, cool. So now let's talk about how a GAN specifically works. As I said, all those applications are generative models specifically. So you can use other generative models. For me, it's GANs. So it's neural networks, black boxes. A neural network, numbers in. Don't worry about what's happening inside. Transformations in some way, numbers out. That's just what I'm looking at. The people that are looking at the inside are the computer scientists. I'm an electronic engineer. I just want these things to do things. So for a GAN, we've got an adversarial game between two networks. So I've got one network, I've got another network, and they're playing an adversarial game. And the way that I like to think about it in terms of the artificial intelligence kind of vibes, it's the left brain and the right brain, right? How are these two interacting with each other? Not going to say it's like this, but possibly in a similar way. So yeah, for the generative neural network, there's two neural networks. So we've got these two neural networks. And he's studying the training data of all of the famous art pieces in the world. And he is actually kind of a thief because he wants to copy those, not copy them. He wants to pretend that he is Da Vinci and he wants to pretend that he found a Da Vinci so that he can sell it. So now he's painting, and he's painting like Da Vinci because he studied all of Da Vinci's artwork, and he makes a painting and he says, hey, check this out. I found a Da Vinci. Can someone give me billions for this thing? But then obviously you can't just say it's a Da Vinci. People come and study your painting to see if it's a Da Vinci. So this is the other neural network, which is called, here it's just a detective. He comes in and he studies, and he's like, no, that's definitely not made by any artist that he knows. It's fake. Right? Again, this conversation of real versus fake. So this is where it gets kind of confusing. The painter then studies the reasons that the detective said it's fake, updates his gradients, and then tries again, right? And the detective comes in again, nope, fake. Artist studies the detective, does it again, until you have kind of an equilibrium between the two. And at that equilibrium, the detective doesn't know what is real or what is fake anymore. And the artist is making photorealistic images. That's the layman's explanation. I keep forgetting to take out that master detective. It's actually quite important. So the painter becomes a master painter. The detective does not become a master detective. At the theoretical equilibrium of GAN, the detective gets completely confused. It literally does not know how to tell real training data from fake, real training data from fake data, generated data, which is where I'm trying, that's kind of strange. I don't know why that happens, but that's kind of the theoretical equilibrium. And it's called Nash equilibrium. It's based off game theory. It's based off economic theory. But yeah, that's the layman's explanation. These two are fighting or playing that game with each other until that equilibrium is reached. Cool, so the painter is called the generator, and again, the detective is called the discriminator. And they play this min-max game over here. So that's where the adversarial part comes in. If anyone does notice it kind of instantly, this is actually a one-class classifier, or a binary classifier, as some people call it. So for a one-class classifier, a binary classifier, you've got labels, which you've got one output node, and you've got a label of 1 or 0. So the log 1 minus over here says make all these images that come from this. Okay, wait, let's look at this. Okay, wait. That Z is the random noise that goes into the generator. That's why you've got a G given Z. And then this log is saying make sure that all the generated images go down. It's labeled as 0. And you can train this as with model.compile, with model.fit if you want to. But then the problem comes in with the adversarial part. And the other side is saying the real images. Okay, we're gonna get to this in very specific detail. The discriminator takes in real training data or fake training data. The fake training data comes from the generator, which obviously comes from the noise kind of going into that. So we've got this neural network, this neural network. This one takes in real training data and fake training data. And it's a 1+ classifier, as in real up, fake down, right? But now, because of this adversarial game here, they're both got the same loss function and not the same loss function. So this discriminator, 1+ classifier, put all the real stuff up, put all the fake stuff down. But this GAN, or this generator side, is saying, please make sure that I'm generating images that this one thinks is real, right? Which is, in essence, if you want to think about it in kind of an end-to-end way, it's saying that from the input of the generator to the output, kind of they're connected in the middle. Make sure that the generated images which are in the middle are real, even though this part thinks they're fake. But then for that specific training part, only this part can update its gradients. I'm gonna assume that I might have to explain that in a little bit different way as well, but it might come clear as the code is happening. But yeah, that's the adversarial part. You've got the same loss function. The generator is only specific to this first one, but you've got, because the discriminator is maximizing this loss function, it's doing something opposite to the generator, which is minimizing this loss function. I hope that made sense. Did that make sense? Okay, but let's go into the code, and then we should be able to kind of figure out a little bit more. So I'm hoping everyone is kind of familiar with TensorFlow and Keras, and as I said, the model fits in the model what's. So we're not doing that. We're going into because of this whole kind of end-to-end, this part can only update in certain times and this part's updating the other times. You have to dive into the gradients of the neural network training. Okay, yeah, go nuts.
You said that the detective in the analogy does not improve. It doesn't become a master, but does it improve at all as the training goes?
Okay, so in the beginning, the generator is outputting complete nonsense, which the discriminator can very easily tell apart from the real training data, because it's just noise in, noise out. That's training step number 1. But then, say after 10 training steps, the generator is now outputting something that's like kind of similar. You can see it here, right? It starts noise, then it gets kind of similar, and then eventually it gets to something. During that kind of similar stage, the discriminator now has to go and study the real training data even deeper to make sure that it knows what's real and what's fake. And then as it does that, because the generator has access to those gradients, the generator becomes even better. And the discriminators go even better. And the generator becomes even better. And then when it gets to a point where that discriminator just gets lost, because the generators, because it's a generative problem, that generator should be able to get to a point where you cannot tell the two images apart. And at that point, the discriminator's only equilibrium or optimal point is to give 0.5 for both, because that's its best loss function, because it can't tell them apart. But that's theoretical. It's very difficult to get to that. I would even say impossible. Okay, cool. So we're just going to look at just an MNIST kind of as I said, this code is on here. You can go and copy paste if you want, or just go and look at it. So the slides are also available, but the code is online. Just type in TensorFlow generative adversarial network. So import all the kind of stuff at the top, and then just load your data. As I said, we're looking at MNIST. The stuff becomes the stuff gets really, really hard when you start doing like CFAR and SVHN. Like, it becomes really hard. Just run this. And yeah, when we get to the deeper side of it, please do ask questions. But for now, it's just loading in the training data, and here's the normalizing of the data. it's always good for, like, as I like what Ron said, as engineering kind of stuff. Always just normalize between either 0 and 1 or -1 and 1, depending on the output of your discriminator. So you can either use a sigmoid activation function or a tan H activation function, but then you have to normalize accordingly. And then sorry.
Just want to zoom in a little if we can.
Oh yeah. Sure.
Where's it gone? I don't know. Okay, never mind. I don't know how to do it. That's why.
Did it work?
No, I just anyway.
Maybe here, view this one. Can you even zoom in?
I don't know. I mean, you can zoom in.
It's something
Like that. Yeah, that's slightly better.
cool. Okay, so this is just the boring stuff. I'm not using my laptop, so I did not have time to copy paste all of this. Your batch size, your buffer size, I don't even know what that is. Okay, cool. Now, when it comes to making these models, see, this is the generator, right? And this is where you have to be careful with your inputs and your outputs. Your input's actually quite simple. Generally, they always just give 100 points. So it's a vector of size 100 as your input. And then you have a very complicated network. But then you have to make sure that if you're using convolutions specifically, if you're using convolutions or they use conv2D transpose, which is kind of the opposite of a convolution, you have to make sure that your output is exactly the same as your training data size, because both the output of the generator and your real training data goes into the discriminator. So you have to make sure that those two are both equally sized, or you can use padding, or you can use whatever kind of extra stuff that you do want to. To work through this model, I don't actually want to, because the point of it is that this is a very complicated model. It kind of uses all the tips and tricks we have for neural networks, besides RNNs and all those kind of stuff. I'm sure people are using that as well. But it's got batch norms, got leaky radio. It's a very strong model, right? And people have gotten this stuff right with just fully connected models. But this is very interesting to see, because if you've got such a strong model, and here's the discriminator part. Okay, wait, let's look actually. So that's the generator model. That's the one network. And when we train this GAN, when we get to that at the end, it only gives these kind of results, which are actually quite not good. I don't know if I can pause it, but like you can see, you can still tell that apart from the real training data. There's still blur, there's still that kind of stuff. And that's with this very complicated model. That's why GANs are starting to people are getting annoyed with them because they're so difficult. Okay, cool. Now the discriminator side. So as I said, the generator side, you have to make sure that output, as it says here, cert model.output shape is 28 by 28 by 1. If it isn't, then everything else is going to break. So then the discriminator takes just a normal MNIST image, but that image can also be from the output of the discriminator, the generator. And then this can be whatever you need it to be, but the output needs to be one node. So one class classifier, a binary classifier. Cool. So yeah, there are variations of GANs that make them a lot better. It's fascinating to see like TensorFlow using this very complicated model for a very crappy GAN. Cool. So we've got two functions now to make the discriminator and the generator. So we can just make the generator. And then, so here's an example of inferring with the generator. So we make noise, and everyone generally uses just random normal noise. And we have a vector of 100, as I said. And then to infer the generated image, plop that noise through the generator, and then that output is your image. And you can just show that output. And because this thing hasn't been trained, you will get problems with this part. Sorry. Yeah, that part. Cool. Let's just run it all again. So the generator hasn't been trained. So you're giving it random noise in, it's giving you a blurry image out. Makes sense. And then the idea is for that thing to update and update and update until it does not do that. And then for the discriminator, it obviously, if I give it that I can give it that generated image, or I can give it one of the real training data points, and it's just going to output one number, right? And then that can be normalized with the sigmoid, but they're not using it here because you can use it later on. Cool. I am assuming that you guys know a little bit about this stuff, so stop me if something is not right. Cool. Then to train both of them, you use the cross entropy, the binary cross entropy, because you've got just one output at the discriminator. There isn't an activation function in the model, so we're using from logits, and that's going to be our optimizer or our loss function or whatever. I know. Cool. Yeah. Now here comes the two loss functions, and this is now where it gets specific to these two things. So as I said, the discriminator is just a binary classifier. So we've got real images that are going to go through it, just a batch from the real MNIST data set. Fake images, which is a batch of generated samples from the generator, so literally the output of the generator. And we cross entropy TF1s for the real stuff, TF0s for the fake stuff, right? And with this specific thing here, so back in before TensorFlow became Keras backended, you can also just literally say tf.math.log of the one output minus tf.math.log1 minus the other output. Exactly the same thing, but use these things because TensorFlow does some funky stuff on the side to do that. But now, so that's the discriminator. That's just a one class classifier, right? Simple. But now here's the generator's loss function. The generator's loss function is specific to the discriminator's output. So here we had the fake loss. We put fake images through the discriminator and we get the fake output, right? And we had the labels as 0. For the generator, we do the exact same thing. Fake output as in generated images through the discriminator, but then our labels on our 1 for the generator. And that's that adversarial game that's being played. Their labels are opposites, literally. And because of that, they both kind of fight each other to do something opposite. That's just a function for the showing of the images. And then we need an optimizer like that. And then now we get to the unraveling of the, do I need this? I probably do need this. The unraveling of the gradients. And for those not familiar with tf.gradient, this is your introduction. Okay, so this is going to be a function for every single training step. Okay. So every single training step, not each epoch, literally every single update. First, we need noise because we need to give that to the generator, right? And then we can, it's over here. I'm going to leave this here, but there's the generated images where I give the noise, right? But now I need to unravel the gradient by I use this function called tf.gradient tape. And what that does is it gives you a little bit more freedom with where the input and the output have gone, because it gives you a tape for every single input and output you made so that you can call that later when you're calling your loss functions. So we make one gradient tape for our generator, and we make one gradient tape for our discriminator. Then we make our generated images. The reason you have to make it inside this with is that a function? With thing, is because here's where the gradients already start. So I put noise in. Now the gradient's already starting for the generator. So I need to keep track of those gradients, right? Then I can start doing the input and the outputs for real and fake training data. So here's our real output. Plop the real images. Sorry, it goes, that's just every batch of images that you give. So those are the real images. Plop that through the discriminator. Now the gradient tape is focusing on where that's going. Same thing for the fake, but the gradient tape is focusing where that's going. Cool. And then you can call these loss functions that we made up here from inside this function. So here's just your generator loss. You give the fake output, which is kind of confusing because again, the discriminator is being used, but because it's the discriminator of the generated images, that gradient tape is going through both. And then the discriminator is just going through the one. Cool. And then down here is how you end up using your gen tape or your generator tape and your disk tape. You literally get the gradients of the generator and the gradients of the discriminator by saying gen tape dot gradients, give the loss, generator dot trainable variables. And this is actually very useful, not just for GANs. This is useful for when you want to start diving into neural networks, not just train them. Because now you literally have the gradients here, and now you can start tweaking them. You can go start doing spectral normalization, start doing a whole lot of other stuff. So this is an important function for TensorFlow with Keras, is to get that gradient tape. Cool. And then you apply it by just getting so we had two optimizers that we made up here, one for the generator and one for the discriminator. Just that optimizer dot apply gradients, zip those gradients that you got up there, and the generator dot trainable variables. Same thing for the discriminator. Cool. That's the hard part. So if there's any questions specific to that, please ask. But that's the hard part. And that's why I want more people to look into this stuff, because that's actually quite simple. It's quite easy. But when you start diving into more complicated GANs, you definitely need this as well. So they are also making GAN modules and stuff to do different things. Cool. So I'm not actually going to run this code because let's actually see if it does work. Another reason why these things are so difficult is because this thing takes about 760 seconds per epoch. So you can leave it, but this thing literally takes about, yes, as I said, 760 seconds per epoch, and you need to do about 50 epochs before this thing looks like anything. So we can run that on the side. But yeah, that's how to code a GAN. And that's quite simple and easy. So, and if you start diving deeper into it, that's how you start coding deep fakes, and that's how you start doing all this other kind of stuff. But yeah, is there any question specific on the code? Or does everyone understand that? It is actually quite simple. The annoying part is how big these models have to be to get anywhere. And when you start doing CFAR as well, you have to make sure that your output is 3 at the end and all that kind of jazz. But that's just your engineering choices. Cool. So yeah, that's GANs in its baby form, right? And now you can go and code your own GAN. But yeah, that's like all these conversations that are coming together. They're quite confusing. They're quite convoluted because you've got this generator side that does all these fun stuff that everyone's very scared of. But then you've got this discriminator side, which is kind of seems kind of pointless. But then on that generator side, again, what is real? What is fake? Can you trust anything on social media? The implications for warfare and politics, the implications for the simulation theory, blah, blah, blah. But now what I'm looking at is the other side, the discriminator. So in this process of learning, as I said, as the generator improves itself, so the discriminator goes deeper into the lower dimensional manifolds. And because it's going into the lower dimensional manifolds, you actually do get improved classification quality if you make the discriminator a semi-supervised model. So now for a semi-supervised model, so say you've got, so semi-supervised going again, or like it's a supervised problem, but you only have labeled samples for a set amount and everything else unlabeled. So the GAN that I just explained now is a completely unsupervised GAN, right? No labels required whatsoever. But now let's say I do have a couple of labels. How do I incorporate those labels? So you're combining supervised learning with unsupervised learning. So how do I start incorporating those things? Is I take that discriminator and I make it into K categories, not just K categories, but I have to extend it to K categories to even do the classification task. But then I add one extra category, which is the fake category, right? But now with that extra fake category, it becomes quite problematic. But yeah, so you can use that discriminator. That's kind of the point of the other side, not just the generative side. You can use that discriminator to do very high end and high accuracy classification. So you extend it from one node to K plus one nodes, and you normal supervised learning over the K nodes because you have those labeled samples. And then all the fake stuff goes into the K plus 1th node. So you've got K categories, but then all the generated stuff goes into K plus 1th node. I'm not going to get into the coding of that because if you remember this part where this thing does not become a master detective, what happens in the semi-supervised setting when I've got K plus 1 categories, but after a while the generated samples are so realistic that they should actually be classified into K categories. But my training loop is saying put them into the K plus 1 category. So for any general semi-supervised GAN like that, you actually end up getting everything classified into the K plus 1 category because it overfits onto the training onto the supervised samples, and so you don't get any kind of benefit. So what they do is they end up making it not K plus 1 categories. This is in every single semi-supervised paper, which is fascinating, but they never do this. They make it into K categories, and then they label the fake samples into what's known as the 0th category. What the 0th category means, so if you're all familiar with one hot encoded labels, if I've got K or 10 nodes, one of them is a 1 and everything else is a 0. Right? Just general supervised learning with general supervised learning with a one hot encoded labeling. But now, for this part, what do I do with the fake samples? I don't want to put it into the K plus 1 category because eventually it becomes so realistic that it confuses the classifier. This discriminator part actually becomes a classifier, right? So it's not just as 1 or 0, now it's a classifier. And if the samples generated are so real, they need to go into the K categories. They can't have their own category. So the 0th class is over one hot encoded labels. It's 0 across all of them. So then the fake samples pull everything a bit down, which is why it's got a lot of connotations to remove overfitting and to improve generalization. Because you've got these fake samples that are becoming more and more realistic, but they're fake, so they're being pulled down. So then your classifier ends up generalizing a bit more. That's what everyone is doing. So now there's another part to this as well, which I don't even have a slide for. I do have a slide for it. Any other questions on semi-supervised learning? That's the essence of semi-supervised learning with GANs, and they are of the top performers for semi-supervised learning. Yeah, it sounds confusing, but it kind of makes sense as well. So then for the novelty detection side of it, so now my PhD is to use GANs for semi-supervised learning because massive implications for cost. You cannot train a satellite image classifier which has something like 7 billion pixels per image, and there's a new image coming around every single orbit. You can't do that as a supervised classifier. You have to do it as a semi-supervised classifier because you just do not have that many labeled samples. You cannot go and label 7 billion pixels. It's just not possible. Same thing for the cancer images, right? You can get a doctor to go and be like, that one over there is a cancer cell. But what about every single other image? That image has thousands, hundreds of thousands of pixels. He's not going to label every single pixel. So semi-supervised learning becomes a necessity for many applications. But even in that semi-supervised state, novelty detection. So a novel category is one that does not fit your original training categories, right? So if I have K categories, for example, I've got just two, cats and dogs, the typical example for all AI models, cats and dogs, and I give the classifier a picture of a fish. That fish belongs to a novel category. That model never got trained on pictures of fishes. It only got trained on pictures of cats and dogs, but it can't classify the picture of a fish as a novel, as a cat or a dog. It has to be able to say, I don't know what this is. And there comes in that K+1 category again. And this is what I personally believe the most important question in neural network supervised classification that is being completely ignored by most people. If you train a classifier and it gets 100%, but you give it any single other image and it says it's a 7 or it says it's an 8, but it was a Japanese character, then is that AI, is that classifier even useful? Because in most data streaming scenarios, you are going to get completely anomalous, novel data. It's very, very rare. It's called a closed set or an open set. It's very, very rare for you to be set in a closed set where all the categories are known and there isn't ever going to be anything new coming in. And so to address that, you've got novelty detection, where there's two ways to do it. You can have just a novelty detecting model, which is now, if you think about the original discriminator, which has one output, it's got that real fake thing happening. That becomes a very good novelty detector, because even if it outputs 0.5 for both generated images and fake images, it should output 0.0 for anything that doesn't look like the training data, because it looks at that manifold of that training data so well that becomes a novelty detector. And they use that a lot as novelty detection solutions. But if you have a novelty detector like that, it can only detect novel categories. It can only say this is real or this is novel. And this is not real or fake. This is real or it's novel, but trained via the GAN way. And then I would need another classifier on the side, another model, to work in conjunction with my novelty detector to do both of them at the same time. So then I would first pass it through the novelty detector. It would say, this is novel. So then I don't put it through the classifier. This is real. Then I do put it through the classifier. But that's two separate models, which is expensive. I mean, it's not that expensive. So like you can go do that. And that's a very practical solution. But at the same time, like I'm trying to do weird AI stuff. And in our heads, in our brains, one of the first things that babies are able to do is recognize what they do not know. Right? And Confucius said that the art of intelligence is recognizing what you do not know. It's something that humans in today's age struggle with so much with. How many times in conversations do you just guess instead of saying, actually, I don't know? And babies are fantastic at it, and now adults aren't. But yeah, so I'm trying to do it in one network, which is why I'm coming back to the semi-supervised part. So the semi-supervised said K+1 nodes. So it's not that weird one with a 0th vector. This is now K+1 nodes, but I want all the novel categories to go into that K+1 node. Then I have one neural network that's able to say I know or I do not know. And by saying I know, it classifies. By saying I do not know, it puts it into the K+1 category. But then there's problems, as I said, when it comes to the GAN, because those images become so realistic that model training gets completely screwed up. Because if every fake thing is going into the K+1 category, you end up confused. And so I'm trying to get a GAN, if anyone can help me, or look at me, even ask for help. So as I said here, for a generative model, you are matching the distribution of the training data with the generator, right? But there's something called a reciprocal distribution. If there is a chalkboard. So if you have a normal distribution that looks like this. If you have a normal distribution that looks like that, the reciprocal distribution is everything that this isn't. So the reciprocal distribution is very high, where this is very low, and then drops down like that. And in essence, that's what you want for novelty detection. You want to get this reciprocal distribution, because everything that it isn't, not that you actually end up getting everything that it isn't, but if I'm able to generalize that k+1th node to everything that it isn't, then every single novel category, even anomalies, even adversarial attacks, all these problems that these classifiers have get solved. Because now any image that does not match that original, those manifolds of that original training data, push to the side. And then you've got a considerably more practical and useful classifier. And cost effective because you're training under semi-supervised learning. So I'm trying to change the GAN to not match the real distribution, but to match the reciprocal distribution. I have not gotten close. So I'm at the moment, I'm, you guys have noticed, synthesizing multiple works. Synthesizing semi-supervised learning, synthesizing novelty detection, and then in novelty detections, there's two separate parts to that as well. Other people have done this, so if you can try it with a GAN, go nuts. I'm trying, it's not working. Other people have done this, and so this isn't my PhD stuff that I'm specifically talking about, but people are researching how to do this. They've noticed that classifier is just doesn't work properly unless you are able to detect and separate everything. Yeah, I never get further than an hour. No, it was not. That was an hour. But that's pretty much all I have to talk about. If anyone has specific questions or comments or anything, again, when it comes to even being aware of the fact that everything on your phone and everything you see on a screen, if you can't use all your senses, then there is a high chance that it can be fake. And that's going to become worse and worse and worse. And in 20 years' time, you might legitimately be texting. People are already doing it, texting and talking to someone that isn't real because you're too shy to go speak to someone that is real. And this is where, and that's a very dark and deep thing to say, but it's true. It's happening. They're teaching kids how to code now at 4 years old, right? Is coding directly related to anxiety and social anxiety? I don't know. I used to be just playing games the whole time because all I did was code. The only reason I got out of it is because when you do PhD or you do masters, you become a little bit more cocky. So you get you can get yourself out of it like that. But the idea that, for example, that Her movie, right, where the guy falls in love with an artificially intelligent thing, I don't personally believe we should allow that. I don't think we should allow tech to even get to that point. You can have a Siri that helps you with your daily tasks, but get that Siri to start talking to you like ChatGPT, and we will find ourselves with a lot of people sitting in a room. And this is, I don't know if I should have this conversation or not. It's like, are people listening? Are people not listening? I don't want to be like that. So if everyone else is like that, then the world's free. So that's also fine. But it's an important thing, especially when it comes to raising your children. Cool. That's me. Any questions?
Thank you for the talk. What type of effort is going into detecting fake or misusing these technologies? What type of effort is going in? Is it, because you were saying that philosophers aren't really listening, so then is it more of the government's responsibility in terms of bringing awareness, or is the actual technologies going into trying to detect such things?
So when it comes to the question of philosophers, that's just my little kind of side pet project, but that's got to do with the simulation theory and the idea of teaching kids how to code and the idea that like we can't fall in love with robots, that kind of conversation. When it comes to the deep fakes and that stuff, that's a technical question. So there's an entire research field dedicated to detecting deep fakes, but that's a very weird conversation because it's the whole cybersecurity conversation. The more hackers you get, the more anti-hackers you need, but then the more hackers you get, the more anti. So shouldn't there be some regulation that says do not even go into research to make deep fakes in the first place? That's up for your own. That's up for your own take. When it comes to research, there is a massive part to detect deepfakes because people are freaking out, and they use GANs to detect deepfakes, and GANs make deepfakes. It's confusing.
Thanks for the talk. Two questions. First, a simple one. Just so you're saying any classification problem should have an extra output to say, I don't know the but I don't know category. Okay.
It's not every single one. So there are certain situations where the data is closed. For example, anything that's streaming when the data is coming in, then you would need that because you cannot tell the future in terms of the data changing. But then say you have, they call it, there's a specific word for it. Say I'm only looking at a data set. That data set isn't going to increase. That data set is closed. Then you don't really need it. And if you, the open versus closed, you will always get a higher accuracy for the closed stuff because you just don't have to do that I don't know thing. But that data, that new data that comes in, you always need that.
Thank you. Then second question is, so do you think is it even possible to at some point detect if something is fake? Because isn't there a limit to how much we can go in terms of detection? Because there is no real limit in terms of how close a fake becomes to a real work.
Are you talking about the GAN specifically, or are you talking about more high level?
Just in general, considering everything you talked about with detection of fake images.
Yeah. So if at the moment we only have image recognizers and that kind of stuff, maybe text as well, but like we don't have touch, we don't have smell, and we don't have all our senses, right? So when it comes to image, when it comes to on a screen, that's why I say you can detect whether it's fake or not. When it comes to other stuff, if that's what you're asking on a very high level philosophy.
In terms of like say fake videos.
Okay.
I mean, at some point it might be completely indistinguishable what is fake and what is real.
Yeah, so that's why I'm doing this whole shouting at philosophers and politicians thing to make sure, because we will get there, to make sure we don't.
So you're not aiming to get there through research, it's more like through basic regulation.
Yeah, to make sure. So tech wise, we will get there. We might already have gotten there, and we don't know it. But by regulation wise, and what do we allow into society? That's where we can say like, just don't allow it.
Really great talk. Thank you very much. Just in terms of philosophers, if you've spoken to, I think you've spoken to anybody at the University of Victoria in the philosophy department.
They're the ones that know me.
So there's no interest on that side.
No. There is interest. So I don't know if you guys know about the SAK conference. Was held last week. It's a combination of philosophy and computer science, and I was quite heavy in that and driving the fact that has to become big.
What sort of technology is usually used for the sort of detection?
Novelty detection.
Defect detection.
Sorry?
Defect detection specifically.
Oh, as I said as well, it's GANs as well. I'm not gonna, don't take my word for that. I am very deep into that research field, meaning that it's not just GANs that do it. I just know that GANs are doing it. So there could be other stuff.
Does the output of the binary classifier or the discriminator tells the generator why the discriminator thinks it's a fake image or real image?
Yeah.
With just binary classification?
Pretty much. So as I said with the code here, because if you think about it, when for the discriminator, it's just that networks, real images in, fake images out, binary classifier. Dope. For the generator, think of those two networks being connected. Think of one big network, right? Then it goes from the noise to the middle. Don't even have to look at it, to the end of the discriminator, right? But during that update step, the discriminator is frozen. I can only update the generator. That's how because it's that whole gradient, that's how it knows what the discriminator is thinking, but that discriminator is frozen in that step, so that only the generator gets updated.
So it works forward. So from a good image towards a higher quality resolution. Do models exist that work backwards?
First, tell me why.
For example, fakes. If you know it.
Ooh, lower its embedding until you can. It's clever.
No, but I'm also looking at it from a scientific perspective. Like if you could apply it and say, so James Webb Telescope is viewing the space farther and farther to try and see the cosmic microwave. If it's wrong, say you use GANs to try and see further than what James Webb can see.
Yeah.
Can you go back and say, okay, this is where it might have been wrong?
So GANs kind of go from small to image, but a GAN is in essence an autoencoder swapped around. An autoencoder takes an image and takes it to a latent space, right? So you could use an autoencoder to do that. And then the GAN is just kind of like, if you go look at how the GAN and the autoencoder architecture works, autoencoder is also two networks, but the autoencoder has an encoding part, which takes an image, takes it to like that random noise variable that I spoke about that no one understands, and then decodes it back to an image, where a GAN kind of does something opposite. So you could use an autoencoder for that. I'm very wary of people looking into space and using models because, for one, people be dying, so stop looking at black holes. For two, if you're using statistical models to look into the sky, the statistical models start talking to you about the sky. Right? So after a while, you actually don't learn anything new. You learn about what your statistical model is doing. So I'm very wary of that, but that is possible. Yeah.
Hi.
Hello.
As you've shown that technologies at risk from GANs, so is Hollywood also at risk from GANs?
Yes, sir. So again, nuclear weapon or nuclear energy. So this is quite cool. If you have the ability to completely create a movie, right? We're not there yet. Then obviously Hollywood is at danger. But what's the positive side to it? Special effects can now be done across the globe. You don't need all that money. So now for the first time in the next 10, 20 years, Hollywood's going to completely change because now everyone's going to be able to tell their own superhero stories. And everyone's going to be able to do the same special effects that America can do because of this tech. And I'm hoping and betting on South Africa to kind of lead that charge.
So it's conceivable that studios will now be creating their own artificial characters, and you don't even need to have the real actors anymore.
Yeah, exactly. So we most likely will get to a point if they start using this, right? And there's also an application with Netflix that I'll get to now. If they start using this, then we might get to a point where someone like Tom Cruise's face will just get implanted onto anyone. And even though he's an old man, because people want to see Tom Cruise fighting, then he's going to be everywhere. And so, for example, Henry Cavill and all these people, their beauty is going to get kind of ingrained in everything. So it's dangerous, but it's possible. Also with the Netflix thing, right? So with this super image resolution thing, right? Very cool application is if I have a GAN on my TV or I have a GAN at home, then the amount of data streaming I have to do is considerably less because now the GAN upgrades the quality, so I can just send a very low quality image over the internet to the streaming platforms, and the GAN that's there, maybe that gets sent first, and you have a GAN trained on Friends or something. Then the GAN can upgrade the image quality. So now you can kind of solve internet problems as well. That's the other side.
Any more questions?
Cool. I was not joking when I said there's a lot.
Yeah.